recording also. Okay, so first of all, apologies for missing last time. There's some skunk works going on, which is taking some time to settle the lab, and thank you for your patience. Now, there's one thing which I want to discuss with respect to your course. We've covered all of these sessions, but this session, which was specifically there, segmentation used in medical domain unit and its relatives and uses in medical sciences. Now, this is something which I'm not sure I should cover for all of you, because you may not want to learn this, you may not have any use case of this. So this is something I've kept as a delta. So I'll take a poll, or if you want, you can suggest your own ideas of what specific part we should cover here. Segmentation in general we can cover, and we can look at how segmentation is used and what are different algorithms. Definitely we can do that. But do you want it to be specifically medical domain, or you want to be in all general domain? That is why I actually not conducting this session this time. We're going to start with a neural work embedding, actually word embedding, and then we're going to finish the neural network parts. We are going to finish all these parts, then we're going to go back to segmentation, because your capstone may involve segmentation as well. So depending whether we cover it or not. So we can do this, or we can actually cover NLP in much more detail. So you guys get to decide that whether we should go for the segmentation, or we should essentially cover. Now, segmentation is something which we have sort of already covered, because if you remember our mask RCNN, we had the one of the part where one of the end where we were predicting body pose. Same idea can be used for segmentation as well. Now, if you remember mask RCNN, we had our 7 cross 512, and after that we added, let's say we have 15 classes, or let's say 3 classes in segmentation. Okay, and let us draw our output first. What's the output we are expecting? So we are expecting our output to be something like this. So we have 3 classes, so we are expecting 3 channel outputs, and let's say one of the classes is sky, so we are expecting it to and let's say the other class is a mountain. And let's assume the third class is actually a road. Right, so these are the 3 classes we are expecting. And is it connected? Okay. So this is actually the original image. So in the original image we have a mountain and a road as well as sky. But what we want is that when we give this image to our network, we want all these classes to be segmented and given to us in a separate channel, right? This is the expectation. So this is the kind of output we are looking for. Now, in mask RCNN, what would happen is that we reduce down to 7 cross 7. So we reduce down a lot, and then we are at 512 channels. And after that, we would have done, let's say, 1 cross 512 cross 3, right? And that is going to give us these 3 channels. Now you can clearly see the output of these channels can only be 7 cross 7. So segmentation, what part we have not covered is that what all do we need to make sure that we can actually play with, let's say, 224 cross 224 kind of channel. Drop it down to a small number and then increase it back to 224, because this is too small for segmentation, right? So that's the only part which we have missed, and we can of course cover that, but this is completely up to you. So you guys get to decide that if you want to work on segmentation or not. Okay, and if yes, then any specific thing you want to cover, I'm going to cover unit for you. And so it has to be unit because everything is built on top of unit, but we can look at some of the algorithms also, but you get to decide, as I said. And right now we're going to cover start from neural word embedding and the embedding layer. Okay, now so today's session is neural word embeddings, and it is a very important session because this is going to form the basis of nearly all the NLP you are going to do. And this also forms the basis of the next stuff which we are going to cover. Now please remember, the course you are in is not it's not natural language processing. It is still EVA, which means that we are covering all of this from the perspective that we finally want to use this in images. Okay, so we are not going to go very deep in NLP because this is not about NLP. And having said that, I've made sure that this session is pretty much all about NLP, because if you are interested in moving into NLP, you can actually pick what we are covering here and start building your concepts. Now, some of the content actually, what I'm going to cover today is from the one of the first session of END program, which is completely on NLP. But there we don't even cover. This is END program. So RNN and LSTM, which we are going to cover in some detail. There is only one session because there is sort of obsolete for natural language processing, but we are going to go look at them in a couple of sessions here. Okay, now so let's start. So today we're going to cover some basic introduction about what embeddings are, then understanding n-grams and bag of words. Then we have one hot encoding character and word embedding. But I'm excited about the coding walkthrough. We're going to go through some different ways in which the embeddings are used. Now, some of the algorithms are pretty advanced, but we don't have to look at them from that. We have not covered GRU, but we are looking at GRU concept. Imagine your first few sessions in the phase 1, where we wrote literally the first MNIST, and there we had SGD plus our backpropagation plus no grad and all that stuff which was there, right? So the today's session is going to be something like that, but I want to make sure that you're really used to using these embeddings. Okay, now look at this image. This image is you know what this image is, right? This is staff notation. This is how we write music. Now people who don't understand this, people who don't know how staff notation is written, they definitely will not be able to relate of what actually is going on. But people who know how to use it, they not only can read it, they can read it while they actually play that particular music instrument as well, right? So this is our encoding of music. We can encode our music into these characters, and then we can read these characters to decode the music back. Now, how many of you understood this, what is written here? For those who understood, you agree that it conveys the same emotion that your brain feels while reading it while listening to an orchestra. Now, this is something which is interesting, because if you don't know how to read music, this is all garbage. But if you actually knew how to read music, this will actually, you will be playing all of this in your head, right? So it all depends on how good decoding you can actually do. But computers understand numbers, right? We can't give symbols to our computers. Converting a music to a staff notation and then giving it to a computer would mean that we actually have to use convolution neural network to now decode those symbols. So we don't want to do that. So we need to make sure that we can actually give some sort of numbers to our computer so they actually feel comfortable and essentially use them. Now, NLP is an attempt by humans for computers to understand human languages by performing powerful mathematical operations and statistics of words, right? So I'm sure you know what is NLP. I don't need to go there. Now, text is one of the most widespread form of sequence data. It can be understood as either a sequence of characters or sequence of words, but most common to work on the word level. Now, this is very important because I think 2015 and 16, Andre Karpathy wrote one of the first character level RNN for prediction. Now, there are a lot of changes which are happening. If you are interested in NLP, then you need to form your point of view about what kind of architecture you want to follow. So we're going to see some of them today, and one of them forms actually the basic basis of GPT-3 as well, or GPT-1.2. And but in most of the problems which we are looking at in NLP, we are trying to solve it by this particular line. It can be understood as either a sequence of characters or a sequence of words. So that is what text is all about, but that is what we are trying to make our models do. We are trying to ask our model to, why don't you predict the next word, or given this word, what all words can you think of? So there are two different approaches which we are looking at. GPT falls in the first approach, and even though both the approaches are here we are talking about the character level and the word level. For example, if I say HELL, what do you think the next character can be? Now, it can be O, it can be just a full stop as well. So depending on what is the context, it needs to predict the next character. Now, that is something which is not recommended, because it becomes really very hard to predict the next character based on all the characters. Predicting, you might think that it's possible in the word, but it's not possible from the overall context point of view. It loses the context, because now you have to keep a track of a lot of characters as compared to words. So we actually work on the word level. So given particular word, we predict something else. Now, none of the model we work on would truly understand a text in a human sense. This is also something you need to understand, that this might not be true about GPT-3 or the really big models, but most of the models which we are going to work on, they will not understand the words we do, right? And this sort of a philosophy involved in this particular line, we are saying that we are conscious, and that is why we know that what is the meaning of love, what is the meaning of, let's say, empathy, what is the meaning of hate, or all the words we are good with, right? All the words we understand. But I tend to disagree with that. I think that our brain is a collection of billions and trillions of synapses in such a way that we can't roll our heads around them, which means that we are confused. We are in a for loop or while loop, and because we are in this loop, because we can't stop this loop and look at ourselves from outside, we think we are conscious. So I think if we take an AI and we put that in a while loop where it is always talking and always thinking and always learning, then it actually is alive, right? So that's a very simplified way of thinking about it. But still, like, philosophers are going to fight on this line that none of the model we work on will truly understand the text, but it may. Okay. Now, rather, these models can map the statistical structure of the language, so they can know that when we use the word hate, it actually it's a negative word. When we say that I distrust someone, that is also a negative word. And how the model learn this? It's going to go through all the text possible in the world, and it's going to see where all hate is used. Hate will never be used with something which is poetic, right? Something which is on the romantic side. Now, which is sufficient to solve many simple tasks like document classification, sentiment analysis, author identification, and even question answering. Now, this is something which is powerful because, you know, computers can learn fast, and they can learn on a hell lot of data, so they can structure the content inside. Now, there's one more thing which is not mentioned here, which is the topic classification. That is also something which is now coming up these days. Now, deep learning for NLP is pattern recognition applied to words. Till now, we were doing pattern recognition for our for features in the images. Now we're talking about pattern recognition applied to the words. In fact, today we're going to see a code where we'll use convolutional neural network for NLP, right? So we're going to look at that as well. Sentences, paragraphs in much the same way as computer visions for the pattern recognition for the pixels, right? So exactly the same stuff which we have covered, but now we'll have to work with fully connected layers and LSTMs and GRUs and understand how they link internally. Now, like all other natural language deep learning models, don't take the input as raw text, right? And this is what today's session is all about. That how do we actually feed our text to a particular system? How do we, because in images it's easy, right? You just have a pixel value, and each pixel value can be from 0 to 255. We can have 3 channels of RG and B, and depth also if you want, then RGB-D, and we send those 4 channels to our network. But how do we send text to our network? Because text is literally text. It's 26 characters and some special characters, exclamation mark, percentage, question mark. But how should we send them? Because computer does not have inherent understanding of that. So what we are going to do today is basically understand how do we send text. So they only work with numeric tensor. We know this part. So vectorizing text is a process of transforming text into numerical tensor, right? So that is essentially what we're going to do today. Now, this can be done in multiple ways. Segment text into words and turn each word into a vector. This is one of the most followed approach. Segment text into characters and transform each character into a vector. Now, that is something which is you can easily see that segment text into characters. So if I have a word like elephant, I have so many characters there, and I've segmented text into that character and transfer each character into a vector. So now I have not 26 vector, right? So all the words in the dictionary are now going to be 26 vector plus the length of the word, or the number of characters we have in the word. There's something which is not followed, not recommended. Now extract n-gram of word and or characters and transform each n-gram into a vector. Now n-grams are overlapping features of multiple groups of multiple consecutive words or character. We're going to look at n-gram slightly in more detail, but essentially these are the 3 ways in which we can do it, in which we can convert our words or text into some sort of tensor, right? What are these 3 ways? First way is to take our word and convert that word into a vector. So okay, but we can have many different words, right? Because let's say I am Chindian, which means I am Chinese and Indian also. So my vocabulary might involve Chinese, Hindi, and English, right? And a bit of Kannada also. Now, if I take all of them and make a dictionary, it's going to be a huge dictionary. So how do we transform text into, or let's say, how do we transform text into words? Okay, with words basically. So how do we transform words into this new vector? So you can see that there's a limitation here. I have to decide how many words I'm going to play with. So So let's say we pick 50,000 words. 50,000 is a hell lot of word. For example, Shashi Tharoor might have a 1 million word kind of vocabulary, right? And people who are about to give GRE, they have somewhere around 25,000, right? So 50,000 is a lot of word, but still not good enough to cover everything, because if you just look at Wikipedia, there's so many different words which are linked to different concepts that we literally can't even imagine doing that. So we have to do something better, but we can't increase our word embedding to 5 million also, because if you do that, then the overall learning becomes very difficult. So we need to figure that out. Second, we convert each character into a vector. So we have 26 vectors now, and now we create a new word out of that. And that is something which is not preferred anymore, because it's expensive to train, and it's not performant also as compared to word embedding. And third is that we convert our sentences into n-gram. Now I'm going to speak in n-gram now, okay? So I'm going to read this sentence in n-gram, okay? And my n is 3. Extract n-gram of words, of words or character comma and transform each. I hope you get the idea. I hope you don't want to go through this boring thing, but you got the idea. N-gram basically means taking 2 or 3 or 4, but that's n words together and creating a vector out of that. So this is another approach, and again not followed, because now this is too powerful for us to ignore or not proceed ahead with, and none of the other methods are actually showing any improvement over the word level embedding. Now, collectively, the different units into which you can break down the text, words, characters, or n-grams are called tokens, right? And breaking a text into such token is called tokenization. So first step is going to be we take the text and we convert into a token, and the second step is going to be take the token and then convert that to embedding, right? So we're looking at two different things here. Now, why are we looking at two different things here? Why can't we just convert our why can't we just convert our words into, let's say, vectors directly? Why do we have to go through this tokenization process? Now, what we are saying essentially is that I'm going to actually, let's say, let me write a line here. So cows are on the road. Let's say we have something like this. So first thing is that we're going to convert them into tokens, right? And how do we convert them into token? I'm going to basically look at my 50,000 words which I have, right? Those 50,000 words are the words in my dictionary. I have to pre-decide that what words are going to be there, and I'm going to look at cow inside that dictionary, huge dictionary of 50,000 words. I'm going to go see and see, oh, my cow is here, and I'm going to read that number, and then I'm going to say that is, let's say, 15,346. That is where that cow is. Now R going to be slightly on top, so let's say 777. On is going to be somewhere here, so let's say this is 40,400. 41,236, right? The OT here, so let's say 46,000, and road is going to be somewhere in between, so it says 43,333, right? So those are the tokens. And why do we have tokens? First of all, because we can't send our words into the network, right? Our networks won't understand word. It has to be sent a number. Now I'm writing a number here, and you can see that these are decimal numbers, and computers don't understand decimal either. So we have to convert them into some sort of a 0101 kind of structure. Now here where the problem comes in, that how should we send that number, because we know that we can't send this, right? So one method would be that we do one hot encoding, but that would mean that if I'm talking about cow, I'm talking about 0000, all zeros, 1 here, and all zeros all across, right? So for cow, my vector is going to look like 000001, then all zeros 0000 till the end, right? And the length of this vector is going to be 50,000. You can see how expensive this is becoming, right? If I had like 1 million words, I'll have 999,999 zeros. It doesn't make sense. But one hot vectors are they are the easiest method to convert something, right? So convert something into something. So that's one method, but we are going to look at some other way of actually doing this. But you get the idea what problems we are actually looking at, right? So we can't convert into that, so we have to figure out some other way. But the idea is that we can't send our words into a neural network. I can't take this cow and send it to a neural network. I have to send some text. So that's why tokenization. Second, if we agree on kind of tokenization between, let's say, you and me, then we can use that tokenization and test many different algorithms, right? And when we test algorithms, then we can compare which algorithm is better. So that is why we are talking about tokenization first. So we convert our words into tokens, and tokens are going to be some numbers associated with a dictionary. But these are not learned words. These are these are our way of thinking of how should I assign that word a number. That's all. Okay. So that's the first thing. Second is going to be that how do we actually create a relationship between them? How do I, for example, in India, create a relationship that on and road, the distance between on and road, the distance between on and road, or not, let's say not on, okay, maybe let's pick another word, okay, yeah, clean. Okay, so the word is clean. The distance between clean and road, right? And you'll think, what is the distance between what exactly you're talking about? So we're going to go much more in more detail about what I'm talking about right now. But let's say the distance between clean and road is more in India as compared to the distance between cow and the road. Get an idea what I'm talking about, right? That is something which it has to learn from the context, but that is what we want to train. That is exactly how we want the words to be correlated. For example, if we say AI, then we should be able to think about, let's say, machine learning or CNN, right? We are not going to, and this CNN is going, and what is the CNN? This CNN is convolutional neural network, not that the US TV news channel, right? If you're thinking about AI, then we should not be thinking about painting. But if you're thinking about GAN plus AI, then we can think about painting, right? That's the idea, that how do we correlate between the words, or how one word can be thought of linked to some other word. Now, but we have to start with tokenization first, and even in tokenization there are many problems, and we should not look at tokenization as a very simple stuff as I explained, because it can literally be very difficult. Imagine this line, okay, and we had 50,000 words, but imagine this line. The EBITDA of a company was, let's say, 16% less than last year. Okay, so first of all, look at this guy. This guy is not going to be in dictionary. What should we do? Should we give it UNK, which is unknown? Second is that this percentage, what should I do with that percentage? And third is that 16 number. How many numbers can you have? You can have 1, 2, 3, 4, 5, 6, 1 million, 10 billion, right? So first, so you see the problem here. And second is, let's say the EBITDA of a company was 16% less than the last year, and let's say we add inside sick here, and let's change this to E. Okay, so I'm writing THEN, and you know this is wrong, right? The EBITDA of a company was 16% less than last year, and then we write the sick, and the sick, if you don't know why the sick is written, sick is generally written to tell you that I am writing it exactly how the author intended, or how the author spoke, and I know there's a mistake, but I'm writing it because that is how author spoke. That's why we use the sick thing, right? So you have the sick thing, and let's say after this we have this some comments from the author or someone. The EBITDA of a company was 16% less than last year, and then there's a comment which says that, and we have this semicolon also, okay, and then we have the comment that barring his salary or something like that. Okay. So what I'm getting into is that we have all of these special characters all across, right? And they have some specific meaning. Sick is also something which is trying to convey some of the messages. And then we have this percentage sign, and then we have these words, then we have numbers, then we have these words which are short forms or acronyms of something. So now when we look at it, and let's say we had even more complication inside. Let's say the word was not EBITDA, but we had something like this, EBITDA as a 19. Let's say it is supposed to mean something. Now in that case, the dash also comes into picture, 19 also comes into picture. Is this one word, or these are two different words? There are too many problems to be thought about here, right? So tokenization itself is not easy, and you're going to see that today we are going to look at tokenization code, but eventually we are going to start using some species or someone else's tokenization, because they would have thought about these problems and already solved them, right? So tokenization is something which we are going to also borrow. Now, all text vectorization process consists of applying some tokenization scheme and then associating numerical vectors to the generated tokens, right? That is exactly what we just discussed. These vectors packed into sequence tensor are fed to the deep neural network. So when we have tokens for this, let's say even if you look at our example, if you look at our example, we would have taken, we would have gone to our dictionary, right? Our 50,000 word vocabulary, and the would be here, EBITDA nowhere. So let's say U and K. So we're going to say whatever value for TH is. I'm going to write simple numbers, okay? So let's say 32, and then unknown is let's say 100, and then off is let's say 26, and A is definitely 1, companies let's say 16, and so on. You get the idea, right? So we take our sentence and look at each word through our dictionary, and we punch in that number in our vector. So this is what we feed to our deep neural network, right? We don't feed text, we feed the numbers for representing those texts. Now these vector packed into sequence tensor, and this becomes one specific tensor, right? Now in image, when you look at an image, for example, we can decide that all our images are going to be 224 cross 224 in size, right? 224 cross 224 cross 3. But how do I do it with a sentence? Because I can say I am happy, but I can also say I am delighted to be reading with you again. Right, I'm delighted to be reading with you again. Now here 1 2 3, we have 3, and here we have 1 2 3 4 5 6 7 8 9, we have 9, right? So what do we do? Because we need batching to be there, right? If you're not sending in batches, then there are multiple problems. We can't use GPU properly, right? We can't train properly. I can't go through single line of text again and again, right? So there's this problem here. So first of all, this is a sequence of our token, right? And those numbers which are there are going to be sent to a neural network. But the problem is that I can't send our images, you know, right? So this is 224 cross 224 cross 3. That's the image I have. I can't send this image along with this image. Both the images need to be of same size, you know that. So here the problem right now is that I have 3 and I have 9 here. So what I have to do, I have to actually create a 9 vector. 1 2 3 4 5 6 7 and 8, right? And take the 3 values here, which are going to be, let's say, this one and this one and this one, and unfortunately fill the rest of the one with the black. So there's something which is going to be related to the sequence length. We have to take a call on sequence length as we start. So now we have taken 2 calls. First we have taken 50k, which is going to be our vocabulary, and second is going to be how long our sequence is going to be, which means that if your sequence is longer than the sequence which can come in, then you're dead. Right, so you have to make sure that you take a very good one. And the problem is that there are always going to be people like Shashi Tharoor. There are always going to be people like Donald Trump. Donald Trump is going to be 3, and Shashi Tharoor is going to be probably 90 words, right? And you can't do that. You can't base your you can't create your character sequence length based on the longest ones, right? So you have to look at a compromise here. Now that compromise is going to be that you literally count the number of words here, and you see the number of such examples, and you're going to get again this curve. You can't get rid of this curve. This is Gaussian distribution, right? This is normal distribution. You will not be able to get rid of this curve. It might be slightly skewed. It might look like that, but it's still going to be it's still going to look like this only, right? And you'll probably want to pick either this or something like that, depending on how many samples do we have here, right? So that is what it's going to be, and the other samples which are there, you're of course going to be doing very bad on them. Now all vector these vector packed into sequence tensors are fed to our deep neural network. There are multiple ways to associate a vector with a token. In this section I, so the whole of this section is actually written by Francis Schulet, and that is why I mentioned the source. Now if you look at the source is actually this beautiful book. Let it open. We'll present 2 major cases, one hot encoding of tokens and token embedding. So we're going to look at both of them. Now this book is taking long to open, but when it opens, or if you're able to open it, this is a very beautiful book, but unfortunately this book is written in Keras, right? So I'll not recommend it to follow for the coding part, but you can definitely recommend from the point of view of content. So for NLP, it's a very good book. Okay, now let's look at n-grams and bag of words. Now n-grams, as I just mentioned some time back, are a group of n of your consecutive words that you can extract from a sequence, right? Let's read this again from the n-gram perspective. Let's say our n is 2. So how will we read the next line? The same concept may also be applied to characters instead of and of words, right? That is our 2 gram. If this was 3 gram, then we would say the same concept may also, and so on. Now here's a simple example. Consider the sentence: the cat sat on the mat. It may be decomposed falling to 2 gram if our n is 2. This is how we can read the cat. You see so we have 1 gram in 2 grams. The cat sat on the mat and the mat, right? So if you have 3 gram, for example, then you will have 2 gram and 1 gram also inside that. So we'll have the cat sat, and so on, right? So please remember that this is what we do. Now you might think, why would we want to do that? Okay, why would we want to do that? Most of the time, so this goes back to our first line. In fact, I mentioned to you that actually forms the basis of what we are looking at here. It can be understood. Okay, first of all, read the first line. First line is very basic, right? The text is one of the most widespread form of sequence data. Fine, fair enough. Let's forget this line now. Now let's read this line. Text can be understood as a sequence of characters or a sequence of words, but it's most common to work at the level of words, right? So when we say it, we are talking about sequential data and text and the context, right? So context can be understood as either a sequence of characters or sequence of words. And now this becomes important, sequence of words, because we discussed sequence of characters, something we are not going to be using. Sequence of words, if you can start predicting sequence of word, you can start predicting hell, like GPT-3. GPT-3 is just that. GPT-3 is just predicting the next word or next symbol, right? Now imagine that we actually take a okay, so let's say we have this Python list comprehension, and in Python list comprehension, you know that we write something like this: for this and that. Where is that? Yeah, expression for items in items in lists, right? Now imagine you train GPT-3 or just a sequence predicting or the next word predicting model. Now you start with this. Okay, let's say you give this as the starting point, because you have to give some sort of starting point. What will, after learning for, let's say, thousands of epochs, it will start predicting something like this automatically. So it can say for n, it will be n here, a square bracket n for n in some item, right? So you saw that it's very simple what we're just discussing. What we're just discussing is just to predict the next word. But if you start feeding our Python to it, it will start predicting the next character in Python. If you let's say put in JavaScript, it will start predicting next word in JavaScript, and it will also remember it has to end this, right? Because this is in your data set, and in your data set you're going to compare something like this. Now how would we even compare? What should we do? Now what I can do if I want to train my network on this, something like this, is that given this, some sort of word which should come after that. Okay, if that's the case, is that what we're saying? 2 gram, the cat, right? That is what we're saying. That if this comes in, then our model should have predicted something like this also. It should have predicted some word after this as well, right? And for after one word, there should be some other word also, and that word is for now, because this is where we are, which means that this 1, this 2, and this 3, the 3 gram must be predicted. If I can predict 3 gram, then look at the power here. Now I have a square bracket, expression, and for. This is predicted. So let's say this is learned. If this is learned, then what it has to learn now is that this expression for an item. Now this item is something which it has learned. Let's say this is n. Now for n. Now in Python, if you have for something, what is the next word after that? It is always n, right? So it has to learn n. Now we are still at 3 grams. So something in Python, something is in something else, right? It has to predict this as well. Now let's look at here. Now in lists, what should you do now? Now here it has something in something. Something in something doesn't always end with a square bracket in Python, right? But the problem is that it has to predict that, because our n-gram says that I am looking for this. So how do you use n-gram? You create all the possible n-grams, and you make sure your network is actually predicting all possible n-grams, right? And that's how we train our deep neural network for sequence prediction. Now this is why exactly n-grams are still not obsolete, but they are but there are far better methods than using just n-grams. So such a set is called a bag of 2 grams or 3 grams respectively. The term bag here refers to the fact that you're dealing with a set of tokens rather than a list of sequences. Tokens have no specific order. The family of tokenization method is called a bag of words, right? This is the bag of word system. Now there's no specific order. We are not expecting it to predict in specific order, any specific order. Now, because bag of word is an order preserving tokenization method, the tokens are generated understood as set, not sequence. It tends to be used in shallow language processing, rather models with deep learning models. Like, so what are we saying here? Now, if I can build something, as I discussed with you, if I can build something using just predicting the next word, and my context is very small, my context is let's say 3 gram, 4 gram, 5 gram, I can possibly use n gram. But if my context is literally very large, for example, you know what is the topic of the session today, right? It's neural word embedding. That we would not have done, been able to use in gram form, because that's like literally half an hour ago, right? So topic was discussed half an hour ago. So that's why you'll not be using n-grams for very complicated deep neural networks, but for easier networks where you're looking, let's say, sentiment analysis, or even let's say simple Q&A, it will work. But if you're looking for example, document summarization, where you have 4,000 words and you want to convert a document into 100 lines or 100 words, this bag of words might not be the best idea. Now, extracting n-grams is a form of feature engineering, and deep learning does away with this kind of rigid, brittle approach, replacing with hierarchical feature learning. We will not cover n-grams further, right? So n-grams are useful. You should know them if you are looking at NLP, but that's the end of n-gram for us. We have some more content to do on n-gram. Then comes the one-hot encoding of word and character. Now, one-hot encoding is the most common, most basic way of turning out a token into vector. I discussed that with you, that we have 50,000 words and we have a cow there. We are going to look at cow, okay, 0, 0, 0, and 1 there. It consists of asserting a unique integer index with every word and then turning the index integer I into a binary vector of size n. Now, n is the size of the vocabulary, right? As we discussed, we have 50,000 words in our vocabulary. Our 49,999 positions are going to be 0, and only 1 is going to be 1 for the cow at a specific location. The vector is all zeros except for the ith entry, which is 1. Now, look at this example. Now, we are importing numpy as numpy. So samples, we have a sample here. The cat sat on the mat. The dog are my breakfast. Okay. Now let's build a token. So we are initializing it can be a set also. It can be a dict as well. I just, for example, for sample and samples. Okay, I think I missed just the. Okay, for sample and sample. Okay, so for sample and sample, how many samples we have? We have 2 samples here. Now there should be indentation. I'll fix that. For word and sample dot split, so we take this particular particular line, and split that. And for word, so each of the word I'm going to go through. Sample dot split is going to make sure that I can go through each of the word. Now token index word equal to length of token plus I. So what exactly are we doing? We are saying word, the. Okay, so the becomes the key. Now what is that key equal to? Length of the token index plus 1. So we are actually going through our whole text here, and every time we find a new one, because this word can only be associated with one key. One key can only be associated with one value dictionary, right? So that is what we are actually using. Assigns a unique index to each of the unique word. Note that you don't attribute index 0 to anything. We don't do that, right? 0 is generally used for unknown, or sometimes starting off your system also, or starting off your sentences essentially. Max length 10, result equal to np0, a shape 0, length of the samples, max length. I think I'll fix that indentation so it will be clear for you. Now for I, so this is where we're printing essentially. For I in the invented samples, j comma word in the list, and then we put the index out, and we basically print out whole text here. Now, so what we have done here is basically this part is important for word and samples and so if you write, let's say, sample equal to, I'm going to go with only 1. Let's say, let's go with 2 anyways. So these are 2 samples that we have. So now let's say we initialize one dictionary. Now for sample and samples, and then space, then for word in sample.split, that is going to split our sentences. For okay, if word not in token index, what is this line going to do? It's going to make sure that the word is not in index, and when we use it with dictionary, it's actually going to search for the key. So if the key is not in the index, then do something for me. What do I want it to do? I want it to go to the dictionary, token, and then index, and use this word which I am on as the key, and make it equal to the length of the dictionary right now, right? So whatever word comes in, we are going to be scrabbling it. We are not assigning each of the words in a serial order, right? So this is one of the methods. This is not the only method. This is one of the methods. So index plus 1, right? Sample is not defined. Okay, let's add. Okay, now let's look at our dictionary. Okay, so you can see that this got the first one, and even though we got it the second time also, it's only going to look at the first one, because this line, if word not in token index, it's not going to look at, it's not going to allow it to look at the second disk. Now is here, got a second one here, was got 4, right? So you can see there's no ordering here. Awesome is A, should have 1, but that's not the algorithm we're writing. So this is a very simple algorithm where we literally look at the words, we look at it, assign some numbers, and that is why there are many token addition methods, and we can pick any of them. But generally the idea is to pick the ones which are developed by Spacey or something similar, because they would have spent a lot of time to fix these kind of things and make sure that even tokenization has some sort of meaning to it, and removing or throwing away most of the characters or words which are not important. Now then we have character level 1 hot encoding. Now here what we are going to be doing, if you look at this code, again the samples, we are picking the same 2 samples, and I'm not sure all of you know this, so I'm just going to explain this line. Now here we have characters string.printable. When we do that, we are going to get all the ASCII characters. You might know that. And then we are doing token index. This line is something I want to explain. Now, so import string, that is going to give me access to the string. Characters equals to string.printable. And if I look at characters, I have all the possible printable characters, so that is what I'm actually going to be using. Now I want to explain this line, token underscore index equal to dict, zip, and so on and so on. So let's look at zip first. Before that, I want to make 2 tuples. So let's say A equal to 1, 2, 3, and 4, and B equal to a list of, let's say, Rohan, and then Mohan, and then Sohan, and then let's say Rohan. Okay, and I want to do a zip. So I like to, it will give me a zip object. So let's say I do something like this. See what is done? So zip essentially takes 2 lists and it converts them into it can be set 2 sequences. That's the right way to say it. It takes 2 sequences and zips them, right? So I've got 1 Rohan, 2 Mohan, 3 Sohan, and 4 Lohan. That is what is happening here inside. So zip a range. Okay, so range of what? 1 and character length. So I'm starting from 1, and whatever the length of character is, and this character essentially plus 1. So that's the overall length, and with characters. So essentially we are going to be assigning. So let's do the same thing here. So if you look at token index equal to dictionary of zip. Why dictionary? Because whatever I did on top here, this thing, now if I convert this into dict, I would have, like, instead of tuples, I would have now been playing with a dictionary. Dictionaries are slightly easier to play with, right? Now, if you look at what is happening here, so we can say token index equals to dict. Now you know why we need dict. Zip, why do we need zip? We're going to combine two things. Range of what? From 1 to length of characters. How many characters, whatever number of characters you're seeing on top, comma characters. How many closing? 2, 3. Okay. What cannot be interpreted as integer? What am I missing? Okay. Right, so this is what is happening now. So 0 gets 1, and let's look at our characters also. Okay, so you can see that our 0 got 1, our 1 got 2, and our 2 got 3, and so on and so on, right? So this is again a tokenization method. Now max and 50, result 0, the same thing what we have done, so we don't have to go through that again. This is just to print it. Now always use built-in tokens, okay? But the problem is torch text is tough. We are going to see some of the examples today. So prefer PyTorch NLP. So there are two different things. Torch text is linked with PyTorch directly. PyTorch NLP is, you can say, sort of an outsider program for PyTorch for doing one hot encoding of text at the word level or character level, starting from raw text data. You should use these utilities because they're going to take care of a lot of different things, like what special character we should not look at, how do we play with different problems. For example, very simple example. Okay, I go and look at my dictionary, and in the dictionary I see that there's a word cow, and cow is assigned, let's say, 0000010 kind of number. Okay. Invalid token. This works. Sorry. Okay, I have to add it. I can't write binary. Right? Okay, so we can define cow as 000001000B. Hey, this should work. Okay, so I can assign a cow binary number, but what should I assign this cow? Right? It might seem like a very simple example, but the problem is that someone has to take care of that. Someone has to make sure that all, and there's not just one thing, there are many other things also. What if someone would have done something like this? What should you do? Because you're working with programming languages, and we may say something like this, right? So what should we do in those cases? So that is why tokenization something is, it's not very simple, but of course you can build something of your own. But if people have, you're going to invent the same fact that it's a good idea to for a tire to be a circle, right? So you know what I'm saying. You should use these utilities because they will take care of a number of different problems we might have. Now, variant of one-hot encoding is so-called one-hot hashing trick. Now, which you can use for use when the number of unique tokens in your vocabulary is too large to explicitly handle. What we're seeing right now is that if I have a cow, if I have other things, and if I have, let's say, 100,000 or 200,000, what if I have 1 million words? What if I want to actually work with Wikipedia? In that case, I can't have a vector which is 1 million long. Right? Imagine that vector being so long. So what we can do, we can actually convert this into hash, and then we can work with the hashes directly. Not a part of this course, but you get the idea. So we have something like sample here, and again dimension ID 100. Here, if you see, what we're doing is a hash word. Now hash is something which is already inbuilt, which is there in Python, so we don't have to worry about how to create a hash, but basically given a word, it's going to create a hash and give it to you, and you can literally store that. Okay. Now, using word embeddings, this is a second method I was talking about earlier. So we can provide one hot vector and different values to different words after tokenization, but this is something which is actually used a lot more now because of the powers which the dimensions can provide. One hot vector is giving you a lot of dimensions, but we are only using one dimension every time, and that is something which is causing a problem for us. So why don't we actually use word embeddings directly? Now, another popular and powerful way to associate a vector with a word is the use of dense word vectors. the so-called word embeddings, whereas the vectors obtained through one hot vector encoding a binary, right, and they're sparse, which means that out of 40,000 elements, 39999 are going to be 0, and they're only going to be 0 or 1. We can't use any other value there. And very high dimensional, 50,000 or 50,000, 60,000, or depending on the total number of words we have, right, total number of words we have in the vocabulary, so it's going to be pretty high. Word embeddings are low dimensional, so which means that I will not have 50,000 dimensions to handle 50,000 vocabulary, maybe just 10. So they are low dimension and floating point, and I can assign it any value. So I'm not limited now 0 and 1. I can assign it to any particular value. So what we're going to do is that we have this one hot vector which is sparse, high dimensional, hard coded. We're going to convert this into something like this, which is dense, right? You can see how small this is. Low dimension. This is not going to be equal to the total number of words I have. If I have 50,000 essentially, so the numbers you're seeing here is like 49990 zeros and 1 1 only here. But here we have just 1 2 3 4 5 6 7 8 9 here, right? Low dimension, so the dimension is 9, and learn from data. And we're not going to, here we were predicting, here we were acting like mujhe sab pata hai kind of person, where we were actually adding our own numbers here. But when we look at our neural embeddings, the word embeddings, we are going to learn them, right? And this is something which actually changed the NLP to the next level. This is something which has literally converted our neural network from NLP from where it was in early 1990s, in fact 2000s also, and from where we are today, right? This is the basis of literally everything, the word embedding, or converting something into embedding and now playing ahead with those embedding. We're going to see a very beautiful example today where I'm going to show it in the code. Okay. Now, unlike the word vectors obtained via one hot encoding, word embeddings are learned from data. It is common to see word embeddings that are 256, 512, and 102 dimension when we're dealing with very large vocabularies. So now what is going to happen is that till now we were saying that we need to do two things. And that stands true if you're going to be building something from scratch. But today, as you know, we don't build anything from scratch. So if you are building something from scratch, you're going to look at your dictionary. You're going to look at your vocabulary. Essentially, these are a set of documents you have, right? You would have extracted all the text from those documents and put it inside this container. Then you would have sorted it out and removed all the duplicates. And after that is done, you're going to assign it some sort of vector, some sort of tokenization, token vectors, and after that you would assign it some sort of embedding. This is what you would do. But today what happens is that you can go online, and there's this thing called Google, and if you Google it, you can actually search for an embedding directly. That embedding will be the embedding you will download is going to download with its own vocabulary. So it's going to tell you that I have support of these 50,000 words only, right? And this is the embedding with 256 dimensions. This is the embedding with 512 dimensions. And this is 128. I have another dictionary which is built on 100k words, and that also comes in a flavor of 256, 512, 128. Now, of course, the 128 is going to be low in dimension, and 512 is going to be, of course, in high dimension. But the point is that to train a 512 embedding, you will have to train a hell lot more compared to 128, right? Because we want only 128 association between words, but here we are looking at 512 associations. So the idea is that the higher the dimension, better it is, but that is going to be a difficult thing to handle also, because now we have far more numbers of number to play ahead with. Now let's search for some embeddings online. So let's do that. Let's go online. Okay. So if you go on glove, for example, glove is one kind of embedding. Okay, let's see what all we can download here. So I have this pre-trained word vector, that is what we want, right? This is what we are looking for. The data is made available in public, very good, so I can use it. Whose full text can be can be found at, okay? So this is what we are using. We have Wikipedia 2004 plus Gigawatt 5. So look at this, 6 billion tokens, right? We are talking about this tokenization, looking at our English text and converting them into tokens, and we have 400,000 vocabularies, right? 400,000 words built on top, and we have 50 dimension, 100 dimension, 200 dimension, 300 dimension, right? Total 822 MB, just the embedding. That is just the embedding, which itself is 822. And then you have other things also. You have 300 vector, 42 billion, 1.9 million, and 2.2 million, and so you get the idea essentially, right? These are learned from Common Crawl. This is learned from Twitter. And so you get the idea that it will have more Twitter kind of word, it will have more internet kind of word, it will have more Wikipedia kind of word, right? So based on what, how rich you are, you can pick which dimension you want, which particular embedding you want to work at, right? So that's the idea, that we don't have to train it now, we can literally start from here. This is a starting point, by the way, that is not the end, this is just a starting point, because after this you have to train a network. So we get this embedding, and from the embedding we actually start training our networks. Now, okay, so this is what we discussed. There are two ways to obtain embedding. Learn word embedding jointly with the main task, and we are going to discuss this. In this setup, you start with a random word vector, and then you learn word vectors in the same way you are going to learn the weights of a neural network. So basically, what we are saying is that, so look at these two steps. First step is that we have text. We convert our text into tokens, right? And we convert our tokens into this embedding, which is not downloaded, which is just random numbers associated with each token, for example. And then we have some RNN or LSTM, and we have some prediction to be made. Right? And let's keep it very simple. We have only three words, which are hi, how, hi, comma, how are you, and question mark, right? So we have only these four things. So we have this 1, 2, 3, 4, 5, and 6 things which we need to predict. Now, hi, so, and let's say we've assigned these numbers 1, 2, 3, 4, 5, and 6. These are tokens we've also assigned. Now that token is fine, but embedding is now random. So what we're going to do initially, we're going to assign some random, let's say 4-dimensional vector to all of them. Right? These are literally four-dimensional random vectors. Now, which means that if a hi goes in, the first random number goes in, and that so that goes like a text inside a model. I'm supposed to predict this comma, right? So I'm supposed to predict that random number, okay? And then when then this random number goes inside, I'm supposed to predict this random number. Now, if we keep the embedding itself as trainable, what is going to happen is that it's going to say, dude, I can't play with this random number thing. I have to make sure that I know what I can predict, right? So it's going to convert those random numbers itself into a set of sequence, a set of numbers which make sense, right? So if we train our embedding like that, we end up training the embeddings directly. This is how embeddings actually are trained. In second case, we have this text. This text is essentially looked at in the dictionary, right? The dictionary I was talking about, which is coming with Glow. We know that what embedding we're looking for. I directly get the trained embedding, right? I directly get a trained embedding, and then I write my neural network layers, and I predict. Now in this case, when we are going to be backpropagating, we are not going to be backpropagating this, right? We are not going to backpropagate our embeddings, because that is something we have taken from internet, and it is already very well trained, unless you know what you're doing. Now, second is going to be load your model word embedding that are pre-computed using a different machine learning task than you are trying to solve. These pre-trained word embeddings, these are called pre-trained word embeddings, of course, right? But there are two ways: do it yourself or steal it. Now, learning word embeddings from the embedding layer. Now, before we look at it, we're going to take a 5-minute break, but immediately after that, I'm going to explain to you what is an embedding layer, because that is a very important concept, and you really need to know the difference between a normal layer and an embedding layer. Okay, so we're going to take a 5-minute break, and we're going to start from there. Okay, so let's start. So the simple way to associate a dense vector with a word is to choose the vector at random, right? We can literally do that. We can take a number, for example. We can decide that we have these 4 words. So first word is, let's say, hello, and second is how, and third is, let's say, hell, right? And we can decide, and we can assign it some random number. And we're talking about floats here, so I'm going to write just 3 float numbers, so 2.3 minus 4.9, 6.4, and then how we can assign again 3 random numbers. We can say 3.6, 0.9 minus 19, and then we can assign again some 3 random numbers to it. Hell, we can assign let's say 13, and then 0.3 negative, and then let's say 40, or let's say 4.3, right? So you can assign these 3 random numbers, and this is called the dimension of the embedding. That is what we were seeing, 100D or 400D. Right now we have 3D here, 3 dimension, not 100D, but it can be 100. So, but the point is that if this is random, our task is done, by the way, because all we wanted was a unique way of representing a number. And if we are doing something like this, we don't have to literally assign some specific number to our text, right? We don't have to do one hot encoding. We are literally done here. This is it has all the features of what we spoke about. It is dense, right? It is only you can see there's 1, 2, 3, 4, 5, 6, 12 numbers here, right? But if I have 50,000 words, or let's say even 40 words, then this would be very difficult. In fact, because I just have 3 words, or I don't even have to look at these high dimensions, right? Total dimensions are the number of dimension actually comes from the fact that we have far more number of words. So if I have only 1 dimension, I can still represent this, right? So hell is 13, how is let's say 1.3, how is 3.6, and hello is 2.3, right? I'm done. It is low dimension, it is dense, but it's not learned from data. That is why random embeddings are not used. But the simplest way to associate a dense vector within a word is going to be to choose the vector at random. The problem with this approach is that the resulting embedding space has no structure. It has no meaning, right? For example, 2 accurate words. What we would like actually to have here is that interesting. Okay, what we like to have here is, let's say we have lion, and then we have tiger, and let's say we have jeep, and let's say GLC. Okay, now lion and tiger and jeep and GLC. Now lion and tiger are animals, and jeep and GLC are cars, and they're SUVs also, right? Now go back to our GAN session where we're talking about interlinking embedding, where the embedding is actually linked to something which was supposed to be predicted, right? We're using random numbers to predict something, but ultimately every single one of them actually had some sort of meaning. Now in case of lion and tiger, of course we would like them to be different, but let's say let's say this is what neural network has decided, that this part is going to be for natural objects and this part is going to be for the artificial object, right? So for tigers and lions, you can definitely assume that this is going to be very close to 0, and for jeep you know that this is natural, and for jeep and GLC these are going to be 0, right? Dimensions have meaning. Remember the face recognition session where we discussed that if we allow the face neural network to identify a person smiling and has a mustache and is Arabic and is looking down or is unhappy, etc., so we can actually predict far better in terms of face recognition. This is what is happening here also. So embedding each dimension is going to represent something very specific. Now lion and tiger, we know that they are not the same animals, but we like them to be slightly closer to each other. So let's say the 2-legged humans are this thing and 4-legged humans are this thing, let's say, right? So this is going to be very close to 0 because they're not 2-legged, but for 4-legged, little lion is going to be 3.6 and tiger is going to be, let's say, 3.2. Okay, whereas if I now add, let's say, dinosaur, so in case of dinosaur, it is clear that these guys are going to be 0 and 0, right? Because those are man-made or unnatural objects. But this is going to be also 0 because let's say we're talking 4-legged dinosaur, or let's say we're talking about Tyrannosaurus Rex, right? Walks on 2 legs. So this is going to be 0 then. So let's say this is going to be 0.2, right? Why 0.2? Network figures out its own numbers. But this guy, this number is going to be, let's say, 1.3 now, right? Because it's walking in 2 legs. And now let's say we add a human, right? We know that human and dinosaurs, because they walk in a similar way on 2 legs. Tyrannosaurus rex I'm talking about, this is T-Rex. So this number is going to be, let's say, 2.3. You can see that it's closer as compared to, and this is going to be, let's say, 0, and this is 0, and this is 0. Now I can see if I subtract human versus dinosaur, I'm going to get 2.3 minus 1.3, let's say, whole square, and the under root, so 1, right? That's the distance between human and Tyrannosaurus rex. But if I do a human minus GLC, I've not written these numbers. So let's say Jeep is 3, and then 0, and then this is also let's say 3.6 and 0, right? Now if I do a human versus GLC, you can see 2.3 square, okay? So that's some number plus 0 and 3.6, so 3.6 square. So that's going to be 2.3 square plus 3.6 square, 18.25. 4.27. So the distance between human and GLC is 4.27, and of course, right, you are expecting the number to be high, right? You're expecting the distance between human and GLC to be high. But this is we thinking and adding, right? Now what should I do with parrots? What should I do with carrots? What should I do with brinjal? What should I do with let's say rug? What should I do with a pen? What should I do with a computer? So we can't keep on assigning that, right? That is, but you see the structure here. You see that if the embeddings are closer, I can actually extract more information from that. That is precisely what we are looking for. That is why we are not looking for random embedding. But it does most of the work, but it does not do that linking kind of work. The words are, so for the word accurate and exact, right? These are two words which are very close to each other, may end up with a completely different embedding. We would like them to have similar meaning. We will like them to have similar embedding. Even though they are interchangeable in most of the sentences, it is difficult for a deep neural network to make sense for such a noisy, unstructured embedding space, right? We can't always start from a random number. That is why we need an embedding which makes sense. Now, to get a bit more abstract, the geometrical relationship between the word vector should reflect the semantic relationship between these words, right? This is exactly what I drew. Right, this is exactly what I drew. The geometrical meaning and the system is the semantic meaning. Geometrical, basically, you can see that I'm drawing a word here. It's a 4-dimension, right? And in 4-dimension, if I can draw this human and I can draw the GLC, I'm looking at the distances. To keep my life easy, what I'm going to do, I'm going to convert this into 3-dimension. Let's say 2-dimension only, okay? Just to keep my life very easy. So I'm going to remove all of these dimensions. Right, and I should not do that. Okay, let me remove this dimension. So this is a 3-dimension now, right? Now if I were to draw 3 dimensions, this is x, this is y, and this is z, and let's say this is x, this is y, and this is z. Now let me also write it here so I don't forget. This is x, and this is y, and this is z, and now 2.3. So my human is at 2.3. So let's say this is human. Right, and so we have a human here because this is 2.3, and then who's the next one? Next one is dinosaur, 1.3. So this is our dinosaur, but it is some bit on y also. So our dinosaur is somewhere here, right? Human is somewhere here, and then a lion. Lion is at y-axis, 0 in x-axis, and 3.6. So this is our lion, and tiger is 3.2. Then Jeep is no x, no y, it is completely on this z-axis, and there is a 3, and then GLC is 3.6. right? Now if I draw this vector, for example, right, you can see that this vector is very long, and the vector has a meaning, and you can literally see that this vector, so human vector minus our G vector is this particular line, and our dinosaur vector minus G vector is this particular line, and both the lines are similar to each other, again telling us that humans and dinosaurs have more in common as compared to a Jeep, right? So that is what we're talking about here. Word embeddings are meant to map the human language into geometrical space, right? We're talking 3-dimension or 5 and 12 dimensions here. For instance, in a reasonable embedding space, you will expect the synonyms to be embedded into a similar word vector. In general, you would expect the geometrical distances such as L2 distance between any two vectors to relate the semantic distance between the associated words. Same thing we are seeing here as well. What we are seeing here is that the distance between these two guys, distance between human and dinosaur, or for that matter lion and tiger, right, is much less compared to the distance between our GL, let's say a jeep and tiger, right? It talks about how indifferent the words are to each other, or how different they are from each other. Okay, now between any two words a vector to relate the semantic distances. Okay, so this is what we're talking about. We have wolf, dog, cat and tiger. So you can see that wolf is slightly off, but you can see wolf is slightly closer to tiger also as compared to dog and cat, because it's what? It's carnivorous and it hunts and eats, and that is what tiger also does. Tigers and dogs are close to each other from that perspective, because both of them are domesticated and they are not literally hunters. They won't eat us. Wolf and tiger will, but tiger and cat and wolf and dog, they are, look at the axis also, so they are much closer to the x-axis, this y-axis, as compared to these guys, right? So this is how we like to structure our words into some sort of embedding. Now, is there some ideal word embedding space that will perfectly map human language and could be used for natural language processing tasks? Answer is no, and probably we have not come across anything like that yet, right? Because we're talking about defining our words into vectors in such a way that they have encompassed every single possible relationship, right? I was talking about such a complicated relationship here, that wolf and tiger are hunters. We have wolf, tiger, dog and cat. That's the only thing written, but we can make that sense out from this, right? Because that is probably how these two words have come into the language, in English language. But defining complete human knowledge into embedding has not been done yet. It's a very difficult task and everyone's literally trying to work it out. Because if you get the word embedding right, by the way, your GPT-3 and everything else is going to be pretty easy. So we have to, word embedding is the key everything. We are adding our transformers and our GPT-3 models and convolution neural networks on text to make even more complicated network, but embedding literally everything is where it starts from. The word embedding space for English language movie review sentiment analysis model may look different from embedding space for the English language legal document classification model, because the importance of certain words are certain words and how the words are structured in themselves as well, right? So you understand this. If I'm going to train my embedding, which is on English language movie review sentiment analysis data set, that is going to be pretty different from this legal document classification data set. It is a reasonable to learn a new embedding space with every new task. Now, this is what we have in PyTorch. We have torch.nn.embedding, and then we have number embedding integer. We have embedding dimensions. Then we have padding. We're going to discuss that later on. Then we have optional int. We're going to look at that. We have max, norm, optional, and blah blah blah. What are these? So we have num embeddings, which is the size of dictionary of the embedding. How many how many words are there in a dictionary? Then we have embedding dimension. What is the size of each dimension? 100 dimension, 256, 512. Then we have padding. If given, pads the output with the embedding whenever it encounters the index, right? If given, pads the output with the embedding vector at padding index initialized to 0 wherever it encounters the index. Essentially, basically, let's say you have you have selected here the size of dictionary 50,000 and embedding you have picked as something. Now, let's say you have picked some number or some word which is not there in dictionary, right? Or your sentences are short. In that case, what should happen to the rest of the spaces? It's going to look at this padding IDX and it's going to pick that number and mention it there. If you mention 0, it's going to just fill everything with 0. If you mention -1, it's going to fill it with -1, right? So this is something we need to initialize. Then max, norm type and scale type of frequency, not the topic of the day. Sparse, not the topic of the day. But you can guess some of these things, but we need to read slightly more deeper into what is happening here. Now look at this code. We have embedding equal to nn.embedding 10 and 3. What are we saying? We are saying we have 10 as our vocabulary. You can see the tensor size of 10 tensors, and 3 is our dimension. Okay. Now the moment you do that, it is going to be creating a random 10 numbers. Okay, and it's going to assign three random numbers to each of those 10 units. Okay, we have 10 different, so imagine dictionary with 10 items or a list with 10 items, and each item itself is 3 random numbers. That is what is happening here, right? So input equal to torch. Let's do that. Why not? Yeah, we have this here. Okay, so we have Okay, it's a structure, so we have to see how do we extract that. Let's start. Let's continue from here. Now we have this input now. Input is defined as torch long tensor. We have 1, 2, 3, 4 and 4, 3, 5, 2. Now how many dimensions are these? This is one dimension and the second bracket is second dimension. We are sending a 2D vector inside. So we focus on the first vector itself only. Okay. Now we have this one going inside the embedding. This is what is going inside, right? And I think I can do that. Okay. Okay, so we have this embedding. Okay, right, and that is 10.3. That is clear. What we need to do is essentially we take our embedding and send our torch dot tensor. So tensor needs to go in, and let's send a number. So let's say 3, and you're going to see it actually gives out something. Right now, if we send, let's say 3.2, and it says that it needs to be a let's say we send in 1. Now it's going to send something like this, right? So what I want you to see is that if I send in 1 again, hey, someone is not on mute, can you go on mute? It gives me the same number again. If I send 2, we get this particular number, and so on and so on. Okay, so that is what is happening right now. But I want you to focus on, this is the first input vector which goes in. We have 1, 2, 4 and 3. So 1 goes inside the embedding, and that we get 0.0251 minus 1.609 and 0.172. Right, let's focus on 2 here. That's why this 2 is highlighted also. So 2 goes inside the embedding, and we get this number 0.6431, 0748 and 6969. Let's confirm that this is a second you can say batch of numbers going in, and here we have 2 here again, and to get this number 6431 and 0743, same number as here. We have 4 here, which is now 14970, 14970. Now you can correlate, right? So what embedding does essentially is that, and this is not a train embedding right now, this is just a random number generated. So what it does is that for every number which is going in, I will get something out. So let's say we send 20, it's going to say out, you've only given me 10, right? I only have 10 available with me. So if I send 10, it's going to say it's out. Why? Because I have 0 here. So maximum I can go ahead with is 9, right? So you can see that what is going inside now, it's inside is going a number here. So you have to now again tokenize your numbers and then send inside, right? That is how whole thing is going to be linked. So first you have to take your words, tokenize them and send that token inside, so it can actually start learning this. Now you can see the grad function, right? Which means this embedding layer is actually trainable, which means I can train these numbers, right? So initially we are starting with some random numbers here, but finally we want these numbers to make sense. So in such a way that the words have a similar context, similar meaning, exactly what we were discussing here. That why would we want to have a structure, right? And this is why we would like to have the geometric relationship between word vectors should reflect a semantic relationship between those vectors also. Word embeddings are meant to map human language into geometrical space. You would expect synonyms to be embedded into a similar vector space, right? All the mathematical words should be similar, should be together. All the, let's say, Bollywood or song related words should be together, and so on and so on. So this is basically how we use our embedding layer in PyTorch. And then we have something like this. Let's see that what we are doing here is we are again torch manual seed 1, word to IDX, hello 0 and world is 1. Now we are using embed equal to nn embedding 2 and 5. It should be very clear what is 2 here. What is 2 here? We are saying our dictionary itself is just 2 words. Fair enough. What is 5? 5 is what? 5 is the dimension we are talking about. So we have 5 dimension word embedding. Now lookup tensor equal to torch tensor, word to IDX hello and d type torch long. So essentially we are taking a word 0 and 1 essentially, right? And we are converting that into a tensor. That tensor now goes inside as a lookup tensor in the embed, and that gives us some number out, right? So this is what we're going to get out. There should be hash here also. So if the hello embed goes in, hello embed is lookup tensor for hello. So basically the hello embedding for hello is going to be this number 0.66142669 and so on, right? So this is what we do. So this is a tokenization which we have done. So we don't want to do this itself. We are going to be borrowing it from Spacey or someone else. The embedding layer is best understood as a dictionary that maps the index value. And okay, before I proceed here, before I show you the text, I actually want to tell you what embedding layer is. You got an idea of what embedding layer is trying to do. But what happens is basically embedding layer is this box. Embedding layer is heavy, by the way. Embedding layer, let's say we are saying 100 dimensions, so it is having 100 dimensions in this axis, 100 dimensions in this axis, and right, and so this is 100 dimension, and this is vocabulary, and vocabulary is, let's say, 50,000 words. Now what happens is that this acts as our first layer. This thing is going to act as a first layer. So let's say this is our embedding. Hey man. Which is 50 dimensions and then 50,000 words, right? This is what we have. Now what happens is that after this, of course, we will have our neural network. So this goes to a RNN layer and a GRE layer and so on, right? That happens, and then we may branch it out to something, and finally the prediction, we may have some sort of attention vectors all across, and finally we are predicting some output here. So the whole NLP starts essentially, and when we backpropagate, our losses from here. Now backpropagation, the loss is going to go from this route and this route and come here and come here and here. Now here you need to decide, are you training? If you are training, then you will allow the backpropagation. If you're not training, you're going to say, please don't backpropagate me, because I have used it from someone. Okay, but you can see that I have all 50,000 words simultaneously, and I have the 50 dimensions. So what is going to happen is that input word hello comes in. Hello goes inside its embedding layer, and embedding layer gives us one vector. Okay, embedding layer is a collection of all the 50,000 vectors, but it's going to be, it's basically a search engine for you. Hello comes in, it searches and gives the vector out, and when you allow backpropagation, it goes back to that same search result and allows the modification also. Now if you have some words which are never used, those are never going to be backpropagated, because that number was never touched, right? So that is also there. You have a 50,000 word vocabulary, but there are 40,000 words, 10,000 words are never touched. Those words are never going to be backpropagated. So we'll have 40,000 trained and 10,000 not trained. That is why training embedding is very important, because quite possible you have very few samples of some words. That is why we actually borrow these embeddings, because they would have trained it better. So word index, we can't send a word, right? We send a word index and it goes to the embedding layer, and embedding layer is actually going to throw out our mean context vector, or the embedding vector which we're talking about, right? So embedding layer is sort of a search layer. So our data goes in, our text goes in, essentially, as I said earlier, text goes in, it looks up, okay, this is where the text is, and whatever embedding was stored for that particular word is going to be sent to the next layer now, right? And when we backpropagate, we're going to backpropagate here, and we go back and change those numbers also, if you're allowing the embeddings to change. Okay, the embedding layer takes in the input as 2D tensor of integers of shape, samples, and sequence length, right? It takes 2D, and where each entry is a sequence of integer, it can embed a sequence of variable length. For instance, you can feed it in an embedding layer with the previous example batch of shape 30 to 10, batch of 32 sequences of length, 32 sequence of length, or 6415, basically any number. All sequences in a batch must have the same length, so sequences are shorter than others should be padded with zeros. Now this layer returns a 3D floating point. Okay, so what is happening here is that if I send in one number, you can already see this. If I send in one number, right, I'm getting what? I'm getting 2D out, right? This is one number which is coming in, I'm getting a 2D out, right? Now if I send, let's say, hello, how are, if I send in, let's say, hello, how are you doing, right? So I'm sending 1, 2, 3, 4, 5. So I'm sending 5 words together. So you are expecting 5 outputs also, right? So this is one output, a second output, and third output, and fourth output, and fifth output, right? And this is 1 dimension. Now this is 2 dimension, right? And this is just one sentence. I could have sent how the hell are you doing, or what the hell are you doing here, right? So the second sentence goes in, which means that I have to now create a third dimension. right? So two-dimensional input comes in, which is sentences and many sentences. So each sentence with words and many sentences, it goes inside an embedding, and embedding gives us this 3D vector out, which is going to be essentially a batch for all good reasons. Okay, now such a 3D sensor can be then processed by the RNN layer or the 1D convolution layer. Now, when you instantiate an embedding layer, it's weighted, its internal dictionary of the token vector initially random, just as with any other layer in neural networks. During training, these vector layers are gradually adjusted via backpropagation structure, let's place into something downstream a model can exploit, right? This is very important. Something the downstream model can exploit. If your embedding layer is awesome, you don't have to train a lot, literally, you're going to see today. Now, using a pre-trained word embedding, now instead of learning word embedding jointly with the problem you want to solve, right? So this is what we were seeing when we are seeing our glove embedding, for example. Right? So the problem we want to solve. Okay, instead of learning word embedding jointly with the problem we want to solve. What was the problem we want to solve here? Predict the next word, right? That's all what we have done. So intuitive and common crawl, and we just wanted to predict the next word, and that's the problem we solved there, and that is the kind of embeddings we got here. You can load embedding vectors from a pre-computed embedding space that you know is highly structured and exhibits useful properties that capture generic aspects of language structure. Such word embeddings are generally computed via word co-occurrence statistics, using a variety of techniques such involving neural networks and others not. Now, such word embeddings are generally computed using word co-occurrence statistics, right? What is word occurrence statistics? The n-gram. Right, we go back to n-grams and few more modification of that. For example, if you have let's say bracket starting, it should end somewhere as well, right? And such. Now let's look at embedding types. Now word-to-vec is very interesting. The word-to-vec is a shallow two-layer neural network which is trained to reconstruct a linguistic context of the words. It takes in an input a large corpus of words and produces a vector space, typically of several hundred dimensions, depending on. So all of these are word vectors, right? All of these are trying to convert a word to a vec. Space typically of several hundred dimensions, with each unique word in the corpus being assigned to a corresponding vector in a space. This should also be clear. Word vectors are positioned in the word space such that the words that share common context in the corpus are located closely, right? It has a semantic structure also, as we discussed, and it's particularly computationally efficient predictive model for learning word embeddings from raw text, because it's very small. You can see we have only two fully connected layers, two-layer neural network. Now it comes in two flavors: the continuous bag of words and the scriptgram model, right? So what are word vectors? What is word-to-vec? So algorithmically, their models are similar. What is happening here is we take our input and then we try and predict the next word here, right? We see that we have t-2, t-1, t+1, and t+2. We're talking about the location, right? And what is the one word which should be predicted? And this is the one word which should be predicted. Okay, let's look at an example. If I ask you that we are looking at, let's say if I ask you that okay, now I have these three sentences in my database. What word should come here? The dash wasn't working on my laptop, computer, and desktop. There are many words which can come here, right? So I can see that the LCD wasn't working, the mouse wasn't working, okay, the sound wasn't working, and so on. The keyboard wasn't working, right? But you can see the contextually similar actually, right? They're very similar to each other and they should be together. I can't say the dinosaur wasn't working on my laptop. I can't say that I wasn't working, let's say the Mars wasn't working on laptops, right? So you can see that they are contextually already very similar to each other, right? This is what we are intending to do, and this is exactly how we train also. So we try and see what all words can fit in. We go back to our data set and we see whether we have those words or not. If yes, then we give it sweet. Otherwise we say that this is punishment for you, right? So we take common words and we try and predict the other word which should be linked with it. And skipgram is reverse of that. Given one word, what all other words should I predict, right? So we have two approaches. In skipgram, I'm going to actually do a reverse thing where we are going to say that I have, let's say, screen, or let's say mouse, as we discussed, for example, right? In case of mouse, what all should I predict? I should predict laptop, because those are the words I see a lot in my database. I should predict desktop, and I should predict, let's say, cat also, because mouse is cat also, right? But you can immediately see that this mouse is not the same mouse we're talking about. So that is where the embedding actually comes in. That is where tokenization comes in. That is where that is where the vectors actually come in, right? So you can't define one word without the use of some other word, right? So you have to have slightly more complexity there. So each word can have two different meanings. So you can now imagine that dimensions have to have two flavors now. One right hand side for the computers wala mouse, second on the animal wala mouse, right? So you have to think, now maybe we can just trigger one dimension upside down, and that converts this man-made mouse to a natural made mouse, right? So that's the idea. This is how we train our embeddings. Now continuous bag of words predict the target word from the surrounding context words. The cat sits on the mat. Now statistically it has the effect that the CBOW smooths over a lot of distribution information by treating an entire context as one observation. For the most part, it turns out to be a useful thing for smaller data sets. Scriptgram predicts the surrounding context words from the target word. Inverse of CBOW. Statistically, Scriptgram treats each context target pair as a new observation and tends to do better when we have larger data sets, right? And in most of the cases, we have larger data sets. So Scriptgram is something we actually tend to use. Now, how does word-to-vec produce word embedding? Word-to-vec uses a trick you may have seen elsewhere in machine learning. This is something we have covered, and that's why this is the session after we have embedding, after we have encoder-decoder network. Word-to-vec is a simple neural network with a single hidden layer, and like all neural network, it has weights, and during training, its goal is to adjust those weights to reduce the loss function. However, word-to-vec is not going to be used for the task it is trained on. Instead, we'll just take the hidden weights and use them as our embedding, okay, and toss the model out. Now, another place you may have seen this trick is unsupervised feature learning, is where autoencoders train to compress the input vector into a hidden layer, right? And what do we do in autoencoder? We have text coming in and we convert that into a vector, and then we take that vector and then we decompose that into the actual sentence. After it's done training, the output layer is stripped off and only the hidden layer is used, since it has learned good features. And that's a trick of learning the good image feature without having labeled trained data, right? So this is precisely what we have done here. We're going to take our text, we're going to predict some embedding, and that embedding is not supposed to predict the same text, right? So it will be forced to actually learn a proper embedding structure. Now, architecture is similar to an autoencoder one. You take a large input vector, compress it down to a smaller dense vector, and instead of decompressing it back to the original vector as you do with autoencoder, you output probabilities of the target words. Now, first of all, we cannot feed a word as a string or a neural network. You know that. We have to tokenize them. We have to convert them into hot vector. Instead, we feed words as one hot vector, which is basically a vector of the same length as the vocabulary. The hidden layer is structural, fully connected dense layer whose outputs are word embeddings, and the output layer is probabilities of the text. So this is what we do essentially. We have our input vector coming in. We have the hidden layer, so it has some weight, and then we have the softmax classifier for the words which we need to predict, right? Probability that the word at randomly chosen nearby positions abandoned, right? So I have another example, don't worry. The input is network is a one hot vector representing the input word, and the label is also one hot vector representing the target word. However, the network output is probability distribution of target words, not necessarily a one hot vector. So what is happening essentially is that I have a hidden layer weight matrix, and that works like a word vector lookup table, right? So this is all what I'm going to be doing. Now, see what we're doing here. We have the WT coming out, and we actually predict these guys out, right? And this is something we have to build statistically from the data set. So we have 1 coming in, and a 1 in the position corresponding to the word ants. So this represents ants, okay? Now when ants come, and it goes through our neural network, and we predict something. Now how are we going to predict something? Now what is happening here is that the classifier, let me explain it using this. First of all, you have to think about a context vector, and context vector, let's say, is 10 words only. Okay, 10 surrounding words. So what we do is we go to our data set, and in data set we look at ants. We look at, let's keep it 9. We look at 4 words on the left side and 4 words on the right side, right? And we draw the statistics, right? And we just then after doing the statistics, what is going to happen is that we have, let's say, all of these words. all of these words, right? And what you can see that, let's say this word is whole, that would have occurred in our data set, and we're talking about the whole internet here, right? So there's 4.7 GB of data sets, so it's going to be a huge data set. What we see that whole and whole come somewhere nearby, right? So we just write a statistics for that. We just write, let's say it came 3.2 million times in the whole internet of like billions of and trillions of pages. Then this is, let's say, Apple, right? Sometimes it will come, so let's say this is 300,000, right? It was eating apples or something of that sort, or apple tree ant, it might come like that. Let's say Mars, 0, right? And let's say printed circuit board, maybe 1400. Why? Because I've seen ants going inside keyboard and eating something. There is also possible, right? Let's say then we have cancer, right? Again, few. So you can understand that if you look at something like this, you are expecting that for the word whole and let's say what kind of red word is going to have many signatures close to ants and so on. So you can see that we know that this is the kind of and this is what we want to predict also now. So if ant comes in, we want to predict 3.2 million. For whole, we want to predict 300k for Apple and so on. You're going to say that that's weird. Of course that's weird. So what we're going to do, we're going to normalize this. So now we have our vector to be predicted, right? So this is what we want this to predict, and this is whatever number is here, we convert it into softmax classifier and we look at what number should be predicted, right? Okay. And once this happens, we throw this layer away. Okay, this layer is thrown out. So what happens is that ant goes in and we get this output here, right? 300 neuron output. And that is what we are writing here also. So essentially what we have done is we take our deep neural network, we take a text or a word, and we send this word to our deep neural network. Our deep neural network predicts something here, right? This something is now checked with softmax, and softmax we are trying to predict let's say the next word, or what I explained in terms of the context word, right? In both the cases, we are trying to predict some sort of softmax number. We match that, we backpropagate, and in the end, we are training this embedding layer also. Once we are done, we throw this away, right? This part is thrown away, so this is not used. So once this is not used, what is the output of this guy? That is going to be the, let's say, 1024 output vector, which we train on. Now, hidden layer operates as a lookup table. The output of the hidden layer is just a word vector for the input word. More concretely, if you multiply a 10,000 one hot vector by a 10,000 cross 300 matrix, it will effectively just select the matrix of that row, right? So I have this vector now. So basically, one hot vector coming in. If I multiply it with the let's say this 3 cross 4, 1 2 3 4 5, 3 cross 5, right? It's going to literally tell me what is that number. So 10 12 and 19. That is what happens basically. That is what happens basically for in our embedding layer, in the first layer. Now, word2vec is able to compute multiple different degrees of similarity between the words, such as semantic and syntactic, because that is how we train it. Now, man is to woman as brother is to sister can be generated through algebraic comparison. We can actually look at this comparison where brother minus man plus woman produces a result closest to a vector representing a sister. You can see some examples here: man, woman, and king and queen, right? So they have a similar geometrical relationship. The dimensions are slightly similar, so it gives us more idea of how these worlds are. Spain is closer to Madrid. Italy is closer to Rome. So if you take this vector and add to Germany, for example, if you take the Italy vector and add to Germany, we should expect Berlin. Now, training algorithm, the word2vec model can be trained by a hierarchical softmax or a negative sampling. We are only going to look at the softmax part where we have the prediction layer. So history comes in and we want to predict mat, right? This is another way. We are not predicting context, we are directly predicting the next word. So the cat sits on the comes in and it has this encoded vector, and this encoded vector is supposed to predict mat, right? So this is how we actually train our word2vec. So this is how the samples are going to be. So the goes in and we are supposed to predict quick. Now the quick goes in, right? It is supposed to predict brown. Brown goes in, supposed to predict fox, and so on. So you can see the training samples are going to be the brown, the quick, the brown, right? The quick, the brown, and then we have quick, the quick, brown, quick, fox. And these are words which are close to each other. Then we have brown, the brown, quick, brown, fox, brown, jump. So you get some idea that these are the words which are close to our data set, and we can literally use them. So you're using a 2 gram here. Now, coding walkthrough. Now, first of all, let's look at the basics part. Now, this is on PyTorch, so I'll request you to spend some time on this particular page. Embedding vector we spoke about. So again, we have an n functional, we have calling an n guy, And same example we saw, we have word hello and word, we convert that in dictionary. The dictionary is now converted into a tensor, and then from the dictionary we grab the value for the hello word goes in as a tensor in our embedding, and the embedding actually gives us our vector, the embedding vector, and that vector right now is 0.614 to 69, and this is a random vector. Right now, an example, n-gram language modeling. Look here, we have context size 2 and embedding size 10, and we have this huge sentence, and we are going trigrams here. We are creating trigrams, and those are stored, and again we are converting our word. So look at this. This is what? This is we creating a this is a list comprehension, but we are using a dictionary here. So for word, I let me show it to you. That will be better. I'm going to write exactly the same line, and vocab set the sentences. This is the sentence. Okay, so let's write vocab equal to set of whatever is inside, and let's write let's say something like this, right? And now we're doing this WTI equals to this now word. Okay, what is word? I'm going to see that now. I, right? What is I? We're going to see that. Okay, so this is what we have. So word I for I comma word, right? So this structure is essentially a dictionary, right? Word and I. What is word? Word is what we're going to get out from the word soon. And for I comma word in enumerate vocab. Now I'm going to show you in a moment of vocab is not defined. Right, so we see W, T and I. It's going to be the dictionary, and it's literally taken everything and converted that into I think I missed something, otherwise this should not have happened. Dot split. Right, the split actually make sure that everything is sent to a different location, and you can see that okay, nonsensical is given 0. Yeah, dictionaries are not in order, so this is not going to be in order also. Right? So this is what has happened. Now enumerate, I hope you know what enumerate is. It's going to give you 1, 2 and 3. Okay, for I am right, so you're getting this 0, 0 also, which means it actually gives you a tuple out. So I can do I comma j print I, which is index, and j. Of course I'm going to get the same thing, but let me write this. The ith element is j. Right, of course the words are the same, but basically it gives you the first location also. Good. Okay, so that's what we've done. So we have created basically our own text, and from our own text we have created our own basically tokenization, and that tokens is something we are going to be sending to our embedding dimension. Now this find, and we find this tokenization we have done. Now we are creating our class. Now this is linear, so you know that embedding is our embedding. Okay, vocabulary size and embedding dimension, something you have to specify. And this is a very simple layer, right? A very simple class, very simple model, nothing special here. So we have our first layer, the embedding layer. Embedding layer is going to get the vector. Then we have the linear layer and linear to out, and finally we have the softmax, and we are predicting our log probabilities. Now what we are doing, we are SGD and nothing special here. You see this trigram, we should tokenize the input, but we all ignore for that. Now build a list of tuples, each tuple is something. Okay, so this trigram is what we're going to be predicting. Now a simple loss function wrapped around that, and when 40 winters shall besiege, right? This is that's the kind of text we are interested in, and essentially if you train it properly, okay, where is the training part? Training log isn't shown. Okay, training log isn't shown. Fine. So what you can see is that it already starts, if you test it out after some time, it actually starts predicting we are to study about our, so we are to study about, so it predicts that, about to the idea study, right? So based on the text we have, it actually starts predicting the next word. So it's pretty simple. I was actually trying to just focus on the embedding part, how the embedding layer is actually used. And you can see clearly the embedding is literally nothing but just simple layer before the embedding layer, okay? So now comes the most important part, which are these 5 beautiful programs. Okay, you can open all of them in 6 beautiful programs actually. Now this is sentiment analysis, and really good work done by this guy. Let's see. Now they're using RNN, so we're not going to look at the RNN part because we have a specific dedication session for that. But what we are going to be doing is we are going to use spacey tokenizer. As I told you that we don't want to build our own tokenizer. We just saw we built our tokenizer, and it's not going to be helpful because a lot of stuff needs to be taken care of. And we have torch text as data, right? And we are using a spacey tokenize, right? So we are using tokenizer as spacey. Now we have this IMDb splits. IMDb is your internet movie database, so you know whether the comment written for the review written for a movie is a positive or negative. That is what we're trying to do here. Now we're looking at some statistics. We have training samples 25,000. Now train sample 0. In the first one we have this is example. Now IMDb dataset only has train and a test split, so we need to create a validation set. So we do that part also. You all know all of that. Not going to look into it. Now word hate this film, the one hot vector is going to be something like this. We know that. We're not looking at that also. Now vocabulary is something like this. Unique tokens to label vocabulary 2. All is fine. I literally want to take you to build the model, and here we are. Okay, this is the model. Now embedding again, input dimension, embedding dimension. We are not borrowing any embedding layer right now. We just borrowed a tokenization. Okay. And if you look at the forward layer, embedding, self-embedding, output, hidden, RNN, and embedding goes into RNN and literally predicts output and hidden, and that's all. Okay, so that's all we're doing. Now this simple model, when given our data set, right here we're training, the data goes in, it hits an accuracy 51%. This validation loss you can see is here and 51% here. That's not really decreasing. It's not great. Now the problem is that why it's not great? It's not great because your embedding layer is literally bad. You're taking one hot vector and putting it into your model, and you're trying to predict something, and you're trying to predict whether it's a positive sentiment or negative sentiment. So if you have 2 classes and your accuracy is 50%, you know your model is bullshitting. It's not doing anything, right? So let's not change it. Let's update the sentiment analysis a bit. What we are going to do, we are going to pack patch sequences, pre-trained word embeddings, different RNN structure, bidirectional, blah blah blah. But this is the most important step, which is where we are going to be using the trained pre-embedding. So exactly the same steps we have, exactly the same steps here, exactly the same steps here, except that we are saying now we are going to be using a glove 6B 100 dimension, right? The one we showed when we saw earlier. Now let me literally, and after that, of course, I'm going to show you the model. Okay, now the model is that we have embedding goes to LSTM and then linear and dropout essentially. If you look at the forward, we have embedding layer coming in, right? That's the output embedded goes in, and then we have the packed embedding sequences. Don't worry on that. This is something we're going to cover later on. But essentially we do something here, and that goes inside our RNN layer, and RNN layer essentially is going to be giving us the output, and the output is added dropout on top further, and we have the final layer, and this is the final fully connected layer, right? Return FC hidden self.fc. Now if you train on that, we are essentially looking at some embeddings here, right? So if you want to see some embedding, that is what you're seeing here. Now when you train the model, and yeah, it hits 87% accuracy, right, from 50% to 87%, and it's a very simple model. We have added literally one LSTM block here, and we are using a pre-trained embedding. Now let's get the third one. Here we have faster sentiment analysis. Now, one key concept of fast text paper is that it calculates the n-gram of an input sequence and append them to the end of the sentences. Here we'll use bigram. Briefly, a bigram is a pairwise word. For example, in a sentence we have how are you, bigrams are how are you, and you, etc. Right? So this slightly more towards how you would think about image augmentation. Is this actually what this is all about? In the previous notebook, we managed to achieve a decent accuracy 84% using all the common techniques used for general analysis. In this notebook, we'll implement a model that gets compare result while training significantly faster and using around half the number parameter. More specifically, we'll be training a fast test. So if you're interested in this particular paper, I request you to look at that model. So there's slight modification here, no modification here. This is where the modification comes in. Again, not our day to cover this, but I'm presenting this because there are many ways of looking at it, and that's why I literally wanted to see what is happening here. Embedding vocab size, embedding dimension, padding ix. Forward is embedding layer, goes to permute. Okay, what are we permuting 0, 1 and 2. Okay, so what actually goes in, right? 3 words are actually going in. So 3 words comes in, and we are actually this is the sentiment. Yeah, so 3 words actually go in and we are permuting them, and then we are actually adding embedded shape. Just read the code, you'll get exactly what is happening. So we are actually using a words, we are permuting them and sending it to words. So we are using the CBOW kind of approach, right? And the other approach, we will send multiple words and we want to predict something. So we have simplified it, and we don't have any LSTM or any simple block here. But now if you actually train this guy, BC logistics is what we are using, and the accuracy is going to be again somewhere around 85%. Right, it's pretty good because the amount of time we spent here is 5 seconds, and if you look at the log here, it's 27 seconds, 27 seconds, 27 seconds, right? So this is pretty good. Now this one is interesting. This is convolutional sentiment analysis, right? We are going to look at them in slight detail later on, but I just wanted to share that this approach is also there. What we're going to do here is, we have this thing, I hate this film, right? So, and we have 1, 2, 3, 4, 5 dimension vector for each of the word we have. Now what we're going to do, we're going to think of kernel as 1, 2, 3, 4, 5 cross 2, right? So we have this vector, this kernel, which is 5 cross 2, is convolving on I hate and gives this output. And then it convolves on hate and this, it gives this output. And it convolves on this and film and this gives the output. So you have these 3 words together, and if I look at them, this is the output we have. And finally, we can add one layer on top of that further and gives me some output here. And that output is supposed to be negative. I hate this film, right? That is precisely what is happening here. So the model is actually pretty simple. We have the embedding output. Embedding output is again going to be something, a fixed vector. We are using conv2d here. The input channel is I, input channel 1, and output channel n filters, basically 32 filters, 64 filters, how many one you would decide. Kernel size is going to be filter size 0 and embedding dimension, right? Because you can see here that the dimension is not going to be 3 cross 3, so we have to be careful about the kernel size. So count 2D layer, 2D layer, and 2D layer, and finally linear, and drop out. Very close to what we have been doing, right? We take our vectors, embedding vectors, stack them, and literally run through them, right? So we have this, I hate this film, so I have this thing where we have literally mentioned the embedded outputs of the embedded output from the embedding layer, right? So we stack them, we literally convolve to them, and now we have the output ready. Everything you've learned till now is going to be usable here. Your cutout, right, and your dropout, which we are doing here already, batch normalization and all. But here it might not be done here properly, but all of those features are actually, because it's a very simple example. We are doing pooling, etc., and finally we send a fully connected output. And when we train this guy, we get 87%. Not bad. So that is much better than LSTM 76. Now look at the test accuracy 87. I think test accuracy is slightly low here. Test accuracy is 85.39, right? But of course we can train better, and you can see that LSTMs were taking 27 seconds, this guy is taking 11 seconds, but of course you have something in between also which was taking far less number of time. So you can think, but convolutions work here as well, right? Now this is the other one where we have multi-class. Here we are just predicting positive, negative, essentially one class. If you want to predict multiple classes, then it's going to be slightly different. That's all, right? So it's one example for multiple classes. I thought I should have this with you. Here we have, I think, 6 classes, I believe. We have 6 classes, yeah. So we have HUM, entity, description, numerical, LOC, and ABBR. So we are looking at a question answer data set, and we are trying to ask, we are trying to think the question is about humans, about entities, about description, about numerical location, abbreviations. Okay, so we're just asking what kind of question is it. Now after that, exactly same model, so not much difference. So I'm not going to take you through this, but I want to take you through this part: transformers for sentiment analysis. Now there are two transformers actually used here. One, we are actually using a BERT tokenizer. Okay, so again, it's built in transformers, and the BERT tokenizer again used for BERT. BERT is a transformer, so we build a tokenizer, and we also use where is it? These are just example. This is where it starts actually. So we take BERT, we are taking BERT model from pre-trained, and we are taking BERT based uncased, right? This is exactly the tokenizer we also picked. So we are picking both. We are picking the model, and we're picking the BERT tokenizer. So this is embedding essentially, right? So we're using the first transformer as embedding. Now if you look at a model, we have BERT, self BERT equal to BERT, forward makes sense, okay? So we have embed equal to, okay, we do not want to backpropagate our BERT, right? That's going to be expensive. But whatever output we get from embed, we send to RNN, and we take the hidden part. And if it is bidirectional, we add in front and back. Don't have to worry about it right now. Just look at here. Hidden equals self dropout hidden, whatever is coming from here, and it goes as an output, right? So out, what is out? Out is a linear layer. So we have literally a fully connected layer, okay? And again, some condition if it is bidirectional or not. Again, we're going to cover that in the RNN session. Now this is our model, and once we finally train it, look at the accuracy. Look at the time. Each epoch, of course, is 7 minutes 27 seconds. Of course, it's heavy. BERT is heavy, but look at the accuracy. It's 91. Look at the test accuracy, 92. Right? Compared to this guy, which took 11 seconds and 85%, and our LSTM, which took 27 seconds and 85, and something in this guy, a fast training, which is 6 seconds and 85% accuracy. So BERT and all of these guys are really good, but they're heavy. Okay, so these are the 6 models I wanted to share with you. Now from assignment perspective, practice all the 6 collab files. Now, I wanted to spend some time with all of these files, right? And the reason is that we are going to be soon, if you look at the course structure again, as I told you that this is still at a vision perspective. We are not going to be looking at in a lot of text perspective, but we have this 2 session left. We have the next session, RNN and LSTM, and after that the GRU session. But after that, once these 2 sessions are there, that's all the kind of NLP we are going to touch. So we're going to immediately move to our convolutions again. And here also we're going to focus on attention, because attention is important, is picking up, and in fact the next end course which we are designing is completely attention only. Now, and exercise to move any one of these to lambda. So you have the 6 models. Of course, don't move the BERT model, your lambda will suffer, but you can literally move any model, or you can have a drop down also, right? For example, you can say that drop down, select CNN, and look at the accuracy, select something and something, and there's a inference code also, right? So if someone writes something, you can actually get the inferencing code also. So you can literally write that this model is trained on its convolution, and you can do refer the codes back, because these are very beautiful code and people should learn these code as well. You can mention convolution sentiment, faster sentiment, upgraded sentiment, and simple sentiment. You can use all of these 4 drop downs, or use one itself, no worries at all. But I just want you to learn how to move NLP models on cloud, and nothing special here. Word is going to go in, it's going to pre-process and come out. Alright, so that's the session for you. I hope you like the session. If you have any questions, you can start now. What is the meaning by a large model having 17 billion parameter? No, that is the transformers inside. These are the fully connected layers which are inside. What you need to realize is that your VGG is also an embedding creator, right? So we have this VGG, image goes in, right? And we have many layers, and 190 million, oh, I don't remember how many parameters we have in VGG. 138 million. So we have 138 million parameters in VGG, and we don't give the output, we just stop here. So now this is 138 million, a very large model for so it's a very large model having 138 million parameters. Okay, what is the output we display? Output of the model. Okay, output of the model is negative or positive. Sentiment, right? It's sentiment. Do we have a session on transformers? No, you do not have a session on transformers. You don't have a session on transformers, as you can see here. We have GRU, attention mechanism, and attention is all you need. question. We have transformers, but of course this, so compare this transformer with here. Transformer, this is transformer. In fact, all of this is transformer, right? Even in the phase one, we have right from here all transformers. Transformer with linear attention. So we start with basic linear attention. So this is part of this is what's going to be covered here. Here, because we have to cover attention also, right? So attention itself is pretty dense. We start from attention here. We understand the whole part here, and then finally this is attention and transformer. The whole phase two is just attention and transformer, and we have to and we are going to look at it in only one session. And of course we are looking at from making sure that we can use this. When we say attention mechanism, we are actually going to look at the image attention. We are not going to be looking at text attention. Transformer, again from an image perspective, so this is not from the NLP perspective. When we use gradient model like glove, embedding layer should be trained or frozen. What do you think, Manimai? What should we do?
I think you should not freeze it, right? Because
yeah, of course. If you're doing transfer learning, why would you unfreeze that big model? So we don't train embedding which we download from internet. Unless you know what you're doing, unless you have 40 million legal documents and you want to train on them and modify your own. But then I'll download a legal embedding document, legal embedding.
This we can do inside.
Sorry?
Specialized cases like legal things. Let's say it's a combination of text plus Wikipedia text plus legal thing. Those cases we can still do trainings, right?
Yes.
Okay.
Yeah, so if you're going to train from scratch, you will need to make that. I think we were here upgraded. Sorry, it was here. So if you're going to be training from scratch, then you're going to make sure that you're not, you don't end up training here. But please remember, I don't imagine a scenario where you will need to build your own embedding, unless you are changing the language itself, unless you are moving from English to Hindi, or let's say you're going to train on CBSE books. So it's going to be a very specialized case, and even in those cases, even a normal embedding train on Wikipedia might be better, because amount of time which goes into training these things, right, is enormous. you'll not be able to meet the kind of training which these models go through. Alright then, if you don't have any questions, then we'll see each other in the next session. And as I shared, please let me know on what should we do with our segmentation session. Do you want it, or you would like to spend some time somewhere else? Don't tell me that please spend some time on GPT-3 or transformer. We don't have time for that. The topic needs to be easy. I can cover segmentation and so please pick a topic in a convolution domain, right? Don't pick a topic in some other domain. Pick something in vision domain essentially.
Rohan, can we keep it a medical domain only?
No, Rajesh, you're Rajesh, right? You are the only person who's involved in this particular part. I can pass on the reference papers to you, and that is why I actually want other guys to make sure that they want to do the medical part only. I want to cover segmentation in general. Sure, I'll do that. I'll pass on the reference to everyone. I just want to know from other guys that you want to have the segmentation session or not. If yes, then we are going to cover unit. Unit is designed for medical, so you'll have that reference already. And I'm going to share other updated versions of segmentation also. But if you want to completely skip this and want to jump into something else, then I'm open for that. That is what I'm telling you, that if you want to skip segmentation session and add some other session, you can let me know on that. So I'm open to ideas, and this session is going to be here after we do speech to text, right? So after this part, we are going to look at this session. So we have some time. So keep coming, keep sharing your ideas. If no one shares any idea, then I'm going to go back to segmentation only. Audio classification, I can add that. Yeah, you can think about it and add, but I don't know what. So we are doing text to speech and speech to text, and then you can do speech to text, and then text can go inside and neural network embedding, and we can do classifications positive, negative. That's the process we need to follow anyway. So we are doing it indirectly, unless you're saying it's a noise or it's a human or someone else who's speaking. Yeah, multiple systems. So people need to basically look at it. So if everyone agrees or if everyone wants that, we can look at it. Okay guys, we have 5 minutes more. If you have any question, let me know. Otherwise, have a very beautiful time.